In a freezing laboratory light, a long cylinder of ice is lifted onto a table and laid carefully beneath the hands of researchers. It has come from deep beneath the surface of Greenland, from snow that fell before modern nations existed, before factories, before the world had learned to measure itself with any precision. As the core is cut, tiny bubbles appear in the blue-white layers, each one a sealed fragment of ancient air. If you imagine standing there for a moment, listening to the quiet scrape of steel against ice, what strikes you first is not the cold. It is the realization that the atmosphere of vanished centuries is still here, held inside something most people would call empty frozen water. That discovery changed the meaning of ice. The great ice sheets were no longer just distant surfaces at the ends of the earth, no longer only blank expanses on maps or symbols of remoteness and endurance. They became records, reservoirs, and part of the hidden machinery that steadies the planet. Inside them lay evidence of old temperatures, ancient storms, abrupt climate shifts, and worlds with coastlines unlike our own. Once scientists began to understand that the question of melting ice ceased to be a question only about the poles, it became a question about the structure of the world we live in now. The deeper that understanding grew, the stranger the picture became. Ice did not merely reflect climate. It interacted with the waters of the world, influenced sea level, pressed continents downward, and over immense stretches of time allowed them to rise again. It could alter shorelines, redirect currents, and preserve memories of climates no human being had ever seen. What looked fixed was not fixed. What seemed slow was not always slow. Buried in the frozen record were signs that the Earth's systems could shift with a speed that unsettled even the scientists trained to study them. So when we ask what would happen if the ice caps melted overnight, we are stepping into more than a dramatic image of floodwater and maps. We are entering a deeper mystery. What exactly are these vast frozen masses holding in place for us now? And how did scientists come to understand that so much of the modern world depends on the silence of ice? Imagine a shoreline just after midnight. The tide is doing what it has always done, lifting itself in the dark with such patience that almost no one notices it. Streetlights lie in broken ribbons across the water. A buoy knocks softly somewhere beyond the harbor wall. In apartment towers farther inland, curtains are drawn, refrigerators hum, and people sleep inside the confidence of ordinary geography. Their cities have names. Their neighborhoods have property lines. Their roads and stations and seawalls seem fixed enough to plan a life around. Nothing in the quiet surface of that hour suggests that the shape of those places depends, in part, on frozen masses most of them will never see. Now imagine, not as prediction but as a way into the problem, that during this one night, the great frozen margins of the planet simply let go. Not the cracking of one glacier, not a theatrical wall of water rising at the horizon, but the stranger proposition that the ice caps are gone by morning. It is an impossible event, unrealistic in any ordinary physical sense, and that is partly why it is useful. The mind reaches first for flooded streets, drowned skylines, and famous coastlines erased in a single gesture. But almost at once, something more unsettling begins to gather beneath that first image, because the phrase itself is already less clear than it sounds. What exactly have we lost when we say the ice caps? The first surprise is that the planet keeps more than one kind of frozen silence. Some ice is already floating, some rests on land, some forms and disappears with the seasons, spreading thin over polar waters and withdrawing again. Some has accumulated across such vast stretches of time that it feels To human intuition, almost like bedrock. Distance encourages simplification. So we tend to gather all of this into one white mental picture. But the Arctic is not Antarctica. Sea ice is not an ice sheet. A glacier slipping between mountains does not behave like a continent, buried beneath miles of ancient snow, compressed into frozen weight. The language of alarm often smooths these distinctions away. The science begins where that smoothing stops. That matters even before any detailed calculation begins. Ice already floating on water does not raise sea level in the same direct way as ice that has been resting on land. A winter lid across polar waters, however important it may be for climate and ecosystems, is not the same thing as a vast land-bound store of water waiting. If warmed enough to enter the global ocean, yet public imagination rarely lingers on that distinction. One large image is easier to fear. And the phrase melting ice caps carries something older than science inside it. The cold ends of the earth have long invited a special kind of imagination. They have stood at the margins of the known world as blankness, silence, punishment, endurance, remoteness, and sometimes revelation. For centuries, those margins were literal. Northern waters appeared in many European minds as places where ships vanished into weather and rumor. The far south existed, for long stretches of cartographic history, partly as conjecture, a balancing mass imagined more than known. A white space at the edge of a map does something peculiar to thought. It invites fantasy, but it also invites permanence. People project almost anything into it, while also assuming it will remain unchanged because so little is known. Ace, in that older imagination, was not yet part of a planetary system. It was an obstacle, a wall, a test, a punishment for ambition. Sailors feared it because it crushed wood and denied passage. Governments coveted routes that might pass through or around it. Natural philosophers wondered what kind of world could produce such cold at all. When James Cook pushed south in the 18th century, he met pack ice not as a symbol, but as a material fact. A shifting barricade of cold geometry that could halt the ambitions of an empire as effectively as a fortress. The farther he went, the clearer it became that the southern world could not be approached as a blank page waiting politely for description. It pressed back. The cold had structure. The whiteness had resistance. Later generations would do the same in the north, chasing passages through a realm that refused to behave like ordinary water. Ships entered and were caught, drifted, splintered, vanished. Crews recorded pressure ridges, grinding flows, strange light, deceptive horizons, and the unnerving feeling that the surface itself had grown bones. At this stage, ice remained chiefly an adversary. Men measured it because it blocked them. They named it because they needed to survive it. By the 19th century, the white margins of the world were becoming less mythical and more exact. Though never less haunting, expeditions brought back latitudes, sketches, weather notes, and specimens. They returned with stories of endurance, but also with something more important for the history of science: the slow replacement of blankness with detail. Ice ceased to be only a symbol of remoteness and became a thing with textures, seasons, varieties, and motion. It could be charted, compared, classified. Fridtjof Nansen would later allow the Fram to drift with Arctic sea ice because he believed the frozen north itself could reveal its hidden movements. Roald Amundsen and Robert Falcon Scott pushed toward the South Pole through a landscape that felt, to their generation, like the last great test of will. Yet the measurements they and others carried back mattered as much as the heroic stories later told about them. Still, there remained a long emotional distance between measurement and meaning. A person living in London, Calcutta, New York, Buenos Aires, or Bangkok could read about polar expeditions and still feel that the frozen ends of the earth belonged to another order of reality. They were important, perhaps in the way deserts and high mountains were important, grand, dangerous, humbling, but peripheral to the intimate mechanics of daily life. Even many scientists approached them that way at first. The polar regions were hard places, useful places, revealing places, but not yet obviously central places. They were where one went to test endurance, engineering, navigation, nationalism, and eventually meteorology and geophysics. The idea that a night in which the ice vanished could alter the fate of ordinary harbors would have seemed less like science than like extravagant fantasy. For that thought to become meaningful, several habits of perception had to change. People first had to stop thinking of the poles as mere scenery. Human beings are skilled at ignoring remote foundations. We live among immediate causes. The road is there because it was paved. The neighborhood remains because buildings are maintained. The coastline seems durable because our memories are short compared with geology, and our politics are short compared with climate. Much of what supports ordinary life hides in plain sight, too slow or too large to trigger instinctive attention. Polar ice belongs to that category. It does not announce itself at breakfast. It exerts no daily pressure on the skin, no sound in the street, no visible motion from week to week, because it feels absent. It is easy to treat it as irrelevant, because it looks ancient. It is easy to treat it as permanent. So when modern audiences hear the phrase, "What happens if the ice caps melt overnight?" they often enter the question carrying several assumptions already built in. They assume the frozen world is a single thing. They assume its importance lies almost entirely in how much water it contains. They assume its disappearance would matter mainly as a visual catastrophe. And they assume the real consequences would begin at the coast. Yet the question starts to change much earlier. In thought itself, are we speaking of the floating skin of the Arctic Ocean, bright and seasonally restless? Are we speaking of Greenland, where snow has accumulated for so long and with such weight that the island carries one of the great ice sheets of the planet? Are we speaking of Antarctica, a whole continent beneath ice so vast that the mind resists sizing it properly? Or mountain glaciers far from the poles, which are not usually what people mean and yet remain part of the larger story of frozen water on land? Once the question opens that way, it begins to behave less like fantasy and more like an instrument. That is what makes it useful. Its impossibility clears away some of the comfort that realistic timescales allow. It does not tell us what would literally happen by dawn, because ice sheets do not work that way. But it does force a confrontation with what they are already doing for us now. Quietly and continuously, a frozen surface can be mirror, lead, archive, barrier, load, reservoir, and memory all at once. Some forms of ice help regulate how much sunlight the planet absorbs. Others hold sea level lower than it would otherwise be. Others brace yet more ice behind them. Before the science is fully explained, a shift in feeling has already taken place. The white edges of the world are no longer only landscape. They are function. And that is where the deeper story begins. Once the poles were charted well enough to be treated as physical realities rather than noble abstractions, Naturalists and geologists began noticing something stranger still. Ice was not only present at the edges of the Earth, its signatures seemed to be written across places where no such ice now existed. Huge boulders sat in improbable locations. Rock surfaces bore long scratches that suggested grinding forces on a scale difficult to explain. Valleys carried shapes that did not look like the work of rivers alone. Landscapes in temperate regions began to whisper of ancient cold. The world that modern observers took as normal was revealing itself as temporary, layered atop an older Earth, arranged very differently. For now, though, it is enough to remain at the threshold, because the threshold contains the mood of the whole journey. We begin in the dark with a phrase that sounds simple. The ice caps melt overnight. It seems at first like a question about inundation, about maps turning blue, about cities that survive and cities that do not. But the closer we move toward the meaning of the words, the less simple they become. We find ourselves distinguishing one frozen world from another. We inherit the long human awe surrounding the poles, from the days when they hovered at the edge of maps to the age when explorers and scientists began turning whiteness into measurement. And we begin to feel something earlier, generations only sensed dimly, that the distant cold has always been closer to ordinary life than ordinary life was able to perceive. That is why the thought experiment, however impossible, remains so powerful. It reveals how much of our intuition is organized around surfaces. We look at the waterline and think the waterline explains itself. We look toward the poles, if we think of them at all, and imagine them as dramatic backgrounds rather than as part of the world's hidden structure. The question of overnight melting disturbs that comfort. It asks us to notice that apparent stability is supported by distant masses, distant temperatures, distant balances. It asks us to imagine the edges of the Earth not as decoration, but as load-bearing pieces of a planetary design. By morning, in the simplest version of the question, people would run first to the coast. They would look for water. That instinct is understandable, and it is not wrong. But even there, the world is stranger than instinct allows. Water does not respond to ice loss as neatly as a basin filling from a tap. It does not rise everywhere in the same way, or for the same reasons, or with the same timing. The next step is to leave behind the movie image of a uniform flood and enter the more unsettling physics beneath it, where gravity, geography, and the memory of vanished ice begin to change what sea level even means. Where gravity, geography, and the memory of vanished ice meet, the familiar image of rising water begins to lose its neatness. In ordinary thought, the picture feels almost effortless. Add enough water, and the level goes up everywhere at once, like a basin filling in a sink. It is a useful image for daily life, close enough for a glass, a bathtub, or a harbor wall on an uneventful day. But the Earth is not a basin with smooth sides, and the boundary between water and land is not a single universal line. It is a living edge, shaped by currents, winds, temperature, gravity, and the disquieting fact that the ground beneath our feet does not always remain where we imagine it has always been. You can feel this by returning for a moment to the coast at night. Two people stand at two different shorelines, perhaps one in Florida and one in Norway, both looking at dark water beneath a quiet sky. They are using the same words. The tide is high. The water seems closer than it once was. The shore feels altered. Yet those two places are not participating in the same event in the same way. One coast may be sinking, another may be rising. One may be shaped by broad currents that redistribute heat and volume. Another may still carry in its bedrock the lingering upward motion of a world that ended thousands of years ago. To stand at the water's edge is always to stand inside a local story first. That was one of the hardest lessons for science to make intuitive. People had long measured tides for practical reasons, because ships depended on them and ports lived by them. Harbors recorded heights, lunar rhythms, seasonal changes, floods, and unusual surges. For navigators and engineers, such records were part of daily necessity. But practical measurement is not yet a planetary idea. When scholars, surveyors, and later oceanographers began trying to understand longer changes in shoreline position, they met a puzzle that seemed almost philosophical. What exactly was changing? Was the water rising or the land falling? Was a harbor becoming shallower because the level had dropped, or because the coast itself had lifted very slowly through time? The observation was simple. The world behind it was not. In Northern Europe, especially around the Baltic, this difficulty became impossible to ignore. People noticed old shorelines stranded above present water, old ports no longer sitting quite where they should, and changes subtle enough to slip past a single lifetime, yet persistent enough to trouble anyone comparing generations. The first interpretation was straightforward. If an ancient shoreline now stood high and dry, perhaps the water had once been greater and had retreated. That was reasonable. But the Earth keeps more than one way of changing relative position, and over time another possibility emerged. Perhaps the shore had risen instead. That second possibility required a different imagination. Land, to ordinary perception, feels far more permanent than water. A coastline may erode, a cliff may collapse, a delta may wander, but the deeper crust beneath a country does not seem like something that breathes. Yet by the 19th and 20th centuries, geologists were beginning to see that regions once buried beneath enormous ice had been pressed downward by that weight and were still, long after the melt, rising back toward equilibrium. Parts of Scandinavia and Canada were not simply static stages against which changing waters could be measured. They were part of the motion. The old image of sea level as one universal horizontal line became harder to defend once the line itself depended on whether the land below had been bent, loaded, and slowly released. This is where the phrase relative sea level quietly changes everything. It sounds technical, but its meaning is almost intimate. What people experience at a coast is never just the height of the water in isolation. It is the height of the water relative to the land at that place. A person watching a dock flood more often than it did in childhood may indeed be witnessing a rise in the average level of nearby waters. But that same person may also be standing on a coast that is subsiding, whether from sediment compaction, groundwater extraction, tectonic motion, or the long after effects of ancient ice loss elsewhere. Another person on a different shore may see less dramatic change, even while the global average climbs. There is no single human experience of the waterline. There are countless local ones. Once that distinction settled into the science, researchers needed a way to connect local records without pretending they were all saying the same thing. Tide gauges became more than maritime instruments, attached to piers and sheltered basins, often using stilling wells to calm the surface enough for accurate reading. They accumulated decades and then generations of data, yet each remained loyal to its place. It measured the motion of the water against the land on which it stood. It could show trend, rhythm, anomaly, and change, but it could not, by itself, separate the movements of the world into clean categories. To read it correctly, one had to ask what that land had been doing all along. By the 20th century, as scientists tried to think globally, the apparent neatness of mean sea level began to fray in another direction as well. Even if land did not move, the surface of the world's waters would not settle into a perfect shell of uniform height. Winds pile water into some regions and pull it away from others. Temperature changes expand or contract it. Salinity alters density. Currents redistribute mass across basins. The rotating Earth and the shape of its gravity field give the planetary surface a preferred unevenness. A lumpy reference surface far more complicated than ordinary language suggests. The phrase sea level sounds singular. In practice, it is restless, always averaging, always shifting, and then there is the stranger part, the one that seems to reverse common sense the moment it is understood. A great ice sheet does not merely sit on land and wait to melt into distant waters. Because it has enormous mass, it exerts gravitational pull. Over time, that pull draws nearby water toward it, subtly heaping the surrounding ocean higher than it would otherwise stand. Around Greenland or Antarctica, the effect is not something a passerby would notice by eye, yet it is real enough to matter. As long as the ice remains massive, it helps hold a bulge of water close to itself. When that mass is lost, the pull weakens, and the nearby water surface can actually fall relative to what it had been. It is one of those facts that seems built to resist intuition. If Greenland were to lose large amounts of ice, places close to Greenland would not necessarily see the largest rise from that loss. Some would see less than the global average. Some regions near the ice could even experience an initial relative fall, once changing gravity and land motion are considered together. Farther away, the redistributed water would contribute more strongly. The result is not a blanket, but a pattern. Every major ice sheet leaves a geographic signature on sea level change, and when it melts, that signature shifts. This understanding did not arrive all at once. It emerged through the gradual marriage of geophysics, glaciology, and careful measurement. Scientists had to think of ice not merely as frozen water stored on land, but as weight, attraction, pressure on the crust, and a participant in the shape of the planet itself. They had to learn that coastlines answer to distant masses. They had to imagine the Earth as elastic enough to deform under load and patient enough to keep readjusting for thousands of years. The older mental image of shorelines as a simple contest between land and waves gave way to something far more intricate. A coast in the present was also a coast in dialogue with vanished ice ages and with frozen regions still holding enormous power in reserve. You can see how that changes the emotional tone of the subject. A uniform flood is frightening in a direct way. It offers one clear image of danger. But an uneven rise, shaped by gravity and by the memory of ancient ice, carries another kind of unease. It means the future will not arrive evenly. It means neighboring regions may not share the same fate at the same pace. It means historical experience can mislead, because the past behavior of one harbor tells you less than you hoped about another. And it means that some of the most important processes are not visible from the shoreline at all. The coast becomes a place where deep physics shows itself indirectly. Through nuisance flooding, retreating marshes, altered storm reach, salt moving inland, failing drainage, and the slow erosion of confidence in familiar boundaries. Modern geodesy sharpened this picture further. Satellite altimetry made it possible to measure the height of the ocean surface from space across vast areas rather than only at scattered coasts. GPS and related positioning systems allowed scientists to track whether land itself was rising or sinking by millimeters per year. Gravimetric missions added another layer, tracing changes in mass across the Earth system. None of this made tide gauges obsolete. Instead, it changed the conversation between local record and global pattern. A gauge could still speak for a place. Satellites could help show how that place fit into the larger arrangement. The old question, is the water rising or the land sinking, did not disappear. It simply became more answerable. As these tools improved, scientists were able to separate stories that ordinary language had long compressed into one sentence. There is thermal expansion, in which warming water occupies more volume. There is added mass from glaciers and ice sheets. There is vertical land motion from tectonics, sediments, extraction, or rebound. There are circulation changes that raise one basin while lowering another. And there are shifting gravitational fields as the great reservoirs of ice gain or lose weight. When people say sea level is rising, several of these stories may be speaking at once. Science did not make the subject calmer. It made it more particular. It also restored something older and more humbling to the way humans think about shorelines. A shore is not merely where water happens to end today. It is the temporary expression of a negotiation among temperature, mass, gravity, weather, and time. Even the firmest embankment exists inside that negotiation. Even a city that appears built against the water with granite confidence is leaning, whether it knows it or not, into a planetary argument that began long before it was founded. To grasp that is to outgrow the bathtub metaphor at last. A bathtub has fixed walls, a still bottom, and no memory. The Earth has none of those luxuries. And yet, for all the sophistication of modern measurements and models, the roots of this understanding run back to something simpler: the refusal of real landscapes to fit easy explanations. Old shorelines stood where they should not. Harbors changed character over generations. The ground itself seemed to remember burdens no living person had witnessed. Before the most precise instruments, there was the unease of observation. Before the elegant theories, there was a mismatch between expectation and place. That is often how scientific vision begins, not with a grand answer, but with an irritation in the visible world. Follow that irritation far enough, and it leads beyond tide gauges and orbital measurements into a stranger realization. Still, if the land in some regions was rising because immense sheets of ice had once pressed it down, then the Earth people inhabited now was only the latest arrangement, long before anyone asked what would happen if the ice caps melted. A deeper question had already begun to take shape in the minds of geologists and naturalists. What if the world had once belonged to ice on a scale almost impossible to imagine? If the ground in some places was still rising under the long afterweight of vanished ice, then the obvious conclusion was also the most disorienting one. The world people called normal had not always been arranged this way. Familiar valleys, boulders, ridges, and polished rock surfaces might be more than local curiosities. They might be remnants of a climate so different from the present that it strained the habits of the 19th century mind. To accept that possibility required something deeper than a new measurement. It required the admission that the ordinary landscape was not self-explanatory. You can feel the tension of that realization by standing in imagination. Somewhere in the Alps in the early 19th century, a boulder rests where it does not seem to belong, far from any bedrock that could have produced it. Nearby, the stone beneath your feet bears long parallel scratches. as though something immense had dragged across it with slow, deliberate force. Valleys curve in broad forms that rivers alone do not easily explain. There are polished surfaces high above present glaciers, and loose blocks of rock carried beyond the places where gravity or flood seem sufficient. None of these signs is necessarily mysterious in isolation. The mystery gathers when they begin appearing together, across regions, with the persistence of a language not yet translated. At first, many naturalists and geologists did what people often do when evidence resists a single neat explanation. They borrowed from what they already knew. Floods had a long explanatory career in European thought. They were dramatic, mobile, and capable of rearranging the land. Others turned to floating icebergs, imagining periods when great blocks of ice drifted over submerged landscapes and dropped stones as they melted. That had genuine appeal because it used something familiar from the maritime world and extended it inland. It explained motion without requiring entire continents to have been buried beneath land ice. For a time, that was easier to imagine than the alternative. An iceberg is strange, but still recognizable. A glacier is visible, but only in its local setting, confined to valleys or cold extremes. A continental ice sheet is another order of thing altogether. To picture one requires a mind willing to scale up from the known until it crosses into something nearly unimaginable. It means seeing Europe, Britain, and large parts of North America as landscapes once gripped by frozen masses that advanced, ground, transported, and retreated on a scale far beyond anything observed in modern weather. It means replacing the stable temperate world with a lost world of pressure, abrasion, and long duration. The path toward that new imagination did not begin with a single hero, however much later retellings preferred one. In the alpine regions, several observers had already begun to notice that modern glaciers offered clues to older and larger processes. Ignaz Venetz, working in Switzerland in the 1820s, argued that glaciers had once been much more extensive than they were in his own time. Jean de Charpentier followed with careful observations of erratic boulders and glacial traces, developing the idea that ancient alpine glaciers had spread far beyond their present limits. The idea of an ice age did not appear first as a grand proclamation from nowhere. It grew from close regional observation, from people who knew the mountains well enough to recognize that the landscape contained a larger memory than present glaciers could account for. This is how a certain kind of scientific knowledge often forms. A local expert, a road cut, a valley wall, a stone out of place. The signs accumulate before the theory does. In that early phase, much of the intellectual work consists of learning how to trust traces whose implications seem too large for the modest forms in which they appear. Science often begins when somebody refuses to let the oddity remain isolated. The land had been speaking in fragments, and a few observers were beginning to suspect those fragments belonged to one vast story. Then came Louis Agassiz, and with him the idea entered public scientific life with unusual force. Agassiz was already a figure of reputation in natural history before he embraced glacial theory. He had worked on fossil fish and possessed many of the qualities that make a scientific personality effective and controversial at once. He was energetic, ambitious, eloquent, and capable of seeing a broad pattern quickly. He also had a gift for turning an emerging insight into a memorable intellectual event. In 1837, at a meeting of the Swiss Society of Natural Sciences, he presented the argument that much of Europe had once lain beneath an immense sheet of ice. It was a claim sweeping in scale and difficult to absorb all at once. The modern world, he suggested, was standing on the remains of a frozen epoch. Agassiz's role in this story has always carried a double quality. On one hand, he undeniably helped propel glacial theory into wider recognition. On the other, historians have long noted that earlier figures such as Venetz and Charpentier had laid substantial groundwork, and that questions of credit were never simple. Agassiz's force of personality could illuminate a theory and overshadow collaborators at the same time. That, too, is part of the human texture of scientific change. Discovery does not move only through evidence. It also moves through prestige, persuasion, timing, and the unequal visibility of those involved. His glacial vision was striking because it unified many scattered observations under one cause: erratics, striations, moraines, polished surfaces, unusual valley forms. These became intelligible as the work of ice in motion. The landscape ceased to be a cabinet of anomalies and became evidence of an ancient regime. That is one of the deepest satisfactions in science when it succeeds. The world does not become less strange. It becomes strange in a coherent way. The marks belong together. The Earth had once behaved differently, and the signs of that difference were everywhere for anyone prepared to look without the assumptions of the present. Still, coherence is not acceptance. Agassiz's claim was ambitious enough to provoke resistance, and some of that resistance was entirely reasonable. Scientific caution is not always obstruction. To many geologists, continent-scale glaciation seemed excessive, especially when more limited explanations remained available. Icebergs really did transport debris. Floods really did move material. Much of geology in the early 19th century was still negotiating between catastrophist frameworks and emerging uniformitarian habits of thought. Charles Lyell, whose principles of geology had been central in encouraging geologists to think in terms of long processes still operating in the present, played a complicated role here. Lyell was cautious about the broad glacial interpretation, and for a time leaned toward the explanations involving floating ice rather than sweeping land ice on a continental scale. His hesitation was not simply stubbornness. Uniformitarian reasoning had trained geologists to be wary of vast speculative departures from observable causes. Yet there was irony in that caution. The intellectual discipline that encouraged geologists to trust slow, real processes could also make it harder to imagine that those same processes, under different conditions, once operated on a much larger scale. A new idea does not struggle only against data. It struggles against respected habits of mind. That struggle played out differently from place to place. In Britain, debates over glaciation intersected with field geology, drift deposits, and efforts to explain transported material across landscapes that no longer resembled anything glacial in the present. In North America, later observers would find evidence equally difficult to reconcile with ordinary assumptions. The growing strength of glacial theory came not from one decisive argument in one hall, but from a widening agreement across distant landscapes. If Switzerland could tell one version of the story, and Scotland another, and northern Germany another, and eventually parts of North America yet another, then the interpretation gained a geographical force no single valley could provide. Even as acceptance spread, the psychological difficulty remained extraordinary. To say that a glacier had once extended farther down a mountain valley was one thing. To say that huge portions of the northern hemisphere had once been covered by ice was something much more radical. A climate cold enough for that world would not be merely a variation on modern weather. It would be another Earth, with altered vegetation, altered animal ranges, altered coastlines, altered rhythms of life and death. Geology had already been expanding time. Glacial theory expanded imagination. It asked scholars to think of climate itself as historical rather than as a permanent background. Once that door opened, many older assumptions became harder to hold. If cold could once rule so widely, then temperate conditions were not the natural resting state of the planet. They were one phase among others. The present was no longer a neutral baseline from which past deviations could be judged. It was simply the latest arrangement. That may sound abstract, but its consequences were immense. It made later climate science thinkable. It encouraged researchers to treat the atmosphere, the land, and frozen regions as dynamic rather than fixed. It loosened the grip of common sense stability. Fieldwork played a crucial role in this transformation because ice leaves behind a style of evidence that feels both tactile and grand. A glacial polish can be touched with the hand. A moraine can be walked across. A perched boulder can be stood beneath in silence. Its very presence an argument against the ordinary logic of gravity. There is something distinctive about sciences that ask people to think through contact with durable marks. They do not rely only on instrument readings or calculations. They recruit the body as witness. One sees the scratch, the ridge, the transported stone. One compares the modern glacier with the oversized shape of the old valley. Agassiz understood the persuasive power of such traces. He spent time in alpine settings, including studies associated with the R Glacier, and used direct observation of glacial action to reinforce his larger claims. But even here, the story is richer than a neat legend. Charpentier and others had already been doing serious observational work. The emergence of glacial theory was collaborative, contested, cumulative, and uneven. It matters to preserve those complications. The realization that ice had once ruled vast parts of the Earth was not simply a triumph of brilliance. It was also an exercise in learning how to see, how to scale up, and how to resist the authority of the familiar. There was resistance for another reason as well. To accept ancient glaciation meant accepting a world in which climate had altered with a severity that human history offered no comfortable parallel for. Even after geology had stretched the age of the Earth and weakened many literal readings of older chronologies, it was still easier for many educated minds to imagine floods, drifts, or local anomalies than to imagine a planetary climate system moving between enormous states of cold and warmth. The idea felt excessive because nature itself seemed excessive. Gradually, though, the evidence wore resistance down. More field observations aligned with the glacial interpretation. More erratics found their parent rocks far away. More striated surfaces pointed in directions that fit ice movement. More moraines and valley forms matched the action of glaciers at scales beyond the modern. What had first looked extravagant began to look economical. The theory demanded a great deal from the imagination, but it explained still more in return. That is often the turning point in the life of an idea, not when it stops sounding bold, but when it becomes harder to explain the world without it than with it. The effect on human self-understanding was subtle but profound. Landscapes that had seemed stable within cultural memory became temporary configurations inside a larger climate history. Fields, forests, river systems, and coastlines inherited a new fragility. They were still real, still usable, still home. But beneath them lay the knowledge that another arrangement had once prevailed, and might under different conditions prevail again. The planet had a memory deeper than civilization, and that memory was frozen into rock and drift. Ice, once treated as an obstacle at the edge of maps, had expanded into a master agent of geological change. From there, a new kind of curiosity began to form. Once scientists accepted that immense frozen sheets had spread across continents, the next question could no longer be avoided. If such worlds of ice had come and gone, what governed their arrival and retreat? What hidden rhythm, if any, could turn a temperate Earth into a frozen one and then release it again? That question would draw the story away from scratched rocks and erratic boulders and toward an even more ambitious effort: the attempt to turn the history of ice into a kind of planetary clock. Once the marks of ancient ice had been accepted as real, the land grew stranger in a new way. Scratches in rock and boulders carried across countries could tell scientists that frozen sheets had once advanced and retreated, but they could not easily say why. A world buried under ice was already difficult enough to imagine. Harder still was the thought that such worlds might return according to some hidden order. If cold had not arrived as a single accident, perhaps there was a rhythm beneath it, some slow beat larger than weather, larger than memory, perhaps even larger than the surface of the Earth itself. That question changed the atmosphere of the problem. The earlier phase of glacial theory had been grounded in traces you could touch: a valley wall, a moraine, a polished slab of stone. Now the inquiry began to drift upward, away from mountain evidence and toward the sky. The imagination required for that step was unusually demanding. It asked scientists to hold together two scales that do not naturally sit in the same thought: a boulder left in a field by ancient ice, and the geometry of a planet moving through space. This was where James Kroll entered the story, and he entered it from an angle science often prefers only in retrospect. He was not a university prodigy moving cleanly through the expected channels of prestige. He came from a modest Scottish background, had little formal education, struggled with health and finances, and worked a series of jobs before becoming a janitor at Anderson's Institution in Glasgow. Important ideas do not always emerge from the center of a discipline. Sometimes they form in the margins, in libraries entered through work rather than rank, in minds that acquire discipline by persistence rather than inheritance. Kroll read with the intensity of someone who had discovered that books could serve as refuge and instrument at once. He was deeply drawn to philosophical and scientific questions, and he belonged to that 19th century tradition of self-educated thinkers whose seriousness could not be measured by credentials alone. There is a certain kind of scientific personality that thrives on solitude, on long periods of inward construction, on patiently fitting together systems larger than the life immediately surrounding them. Kroll seems to have had something of that temperament. He was not merely gathering information. He was trying to understand how the world held together. By the 1860s, he began developing an idea that would turn the history of ice into a problem of celestial mechanics. The Earth does not move around the sun in a perfectly unchanging way. Its orbit varies. The shape of that orbit, or eccentricity, shifts over immense spans of time. Kroll argued that such variations could alter the distribution of solar energy in ways that mattered for climate, especially when combined with feedbacks involving snow, ice, and the reflecting power of bright surfaces. A colder summer, under the right conditions, could allow winter snow to survive. Surviving snow could reflect more sunlight. Reflection could encourage more cooling. Ice could build upon itself. The thought was remarkable because it reached far beyond the landscape evidence that had grounded the earlier glacial debates. It also treated climate as responsive to subtle forcing rather than only to visible catastrophe. Kroll was trying to connect the smallest changes in the geometry of Earth's path to some of the largest transformations in geological history. Even now, there is something almost dreamlike about that move, as if frozen valleys had suddenly become legible only when placed beneath the silent turning of the heavens. His theory, however, did not arrive as finished truth. It was brilliant, suggestive, and flawed. Kroll placed strong emphasis on high orbital eccentricity and on the idea that colder winters in one hemisphere, aided by feedbacks, could drive glaciation. He also worked with estimates of timing and mechanism that later evidence would not fully support. But those flaws are not mere failure. Much of science proceeds through versions that are wrong in detail and indispensable in direction. Kroll helped establish something more important than any single calculation. He showed that climate might need to be understood as a responsive amplifier of small astronomical variations. That was not easy for everyone to accept. Astronomical theories of climate had an awkward status in 19th century science. On one side, they possessed a grand elegance that could attract mathematically inclined minds. On the other, they risked seeming too abstract, too detached from the observational culture of geology. If one geologist could stand on a hillside and point to striations, another could reasonably ask how a remote change in orbit was supposed to explain a moraine underfoot. The bridge between those scales was not yet secure. Without good dating, without long continuous climate records, and without a mature understanding of feedbacks, the theory remained partly suspended between insight and speculation. Kroll himself lived inside that uncertainty. He gained some recognition, corresponded with important figures, and produced serious scientific work. Yet his position never fully matched the scale of his ambition. There is something quietly moving in that contrast. A man of limited means, reading and reasoning his way toward one of the great organizing ideas of climate science, and still unable to provide the kind of proof that would make the wider scientific world surrender its doubts. His life reminds us that intellectual courage does not guarantee immediate authority. By the early 20th century, the question had not disappeared. It had deepened. If glaciation followed some long rhythm tied to Earth's motions, then the problem demanded more careful mathematics than Kroll had been able to supply. This is where Milutin Milankovitch took up the story. He was very different from Kroll in training and style, more formally educated, an engineer and mathematician by discipline, yet he inherited the same immense challenge. How do you calculate the changing distribution of sunlight across the planet over tens and hundreds of thousands of years, and relate that to the appearance and disappearance of ice? Milankovitch worked with the great astronomical variables that would later become familiar to generations of climate students: eccentricity, axial tilt, and precession. These motions do not simply warm or cool the whole planet in a uniform way. They redistribute sunlight by latitude and season. Milankovitch focused especially on summer insolation at high northern latitudes, because the survival of snow and ice depends not only on how much falls in winter, but on whether summer warmth is sufficient to remove what winter has left behind. If northern summers grow cooler, snow can persist. If it persists, ice has a chance to expand. This was a more refined and more durable formulation than Kroll's, though at the time it still remained a theory in search of decisive confirmation. Milankovitch's work was patient, laborious, and mathematically demanding. He spent years calculating long sequences of climatic forcing before computers could make such labor routine. There is a peculiar solitude in this kind of science. It lacks the visual immediacy of field geology and the public drama of expeditionary work. It unfolds in tables, calculations, and the quiet insistence that a pattern too large for direct observation may still be real if the reasoning is exact enough. Yet elegance alone could not finish the argument. Geologists and paleoclimatologists still needed a dependable record of past climate change, long enough to compare with the predicted cycles. That was the old wound in the theory. Kroll and Milankovitch could propose rhythms, but Earth's past had not yet been read with enough continuity to test them properly. A few traces here and there were not enough. Moraines and erratics could testify that great cold had come and gone, but they could not yield a clean global sequence. The clock had been imagined before the dial was visible. For decades, that gap left room for doubt. Some researchers remained skeptical of the astronomical explanation. Others were willing to grant that orbital changes might matter in some broad sense, while doubting the direct pathway from subtle insulation shifts to massive glacial expansions. The climate system, after all, was proving stubbornly complex. Ice, snow, clouds, atmospheric chemistry, vegetation, currents, and the geometry of continents all seemed to enter the story somehow. The Earth was not a passive receiver of celestial forcing. It was an active interpreter of it. Then, gradually, the record began to lengthen. During the 20th century, researchers learned to recover climate history from sediments laid down in open water, tiny shells of marine organisms, deposited layer by layer over immense spans of time, carried chemical and isotopic information that reflected changing conditions in the past. With improved dating methods and accumulating cores, a new possibility emerged. Earth history might be read not only from glacial scars on land, but from continuous sequences laid down far from former ice margins. This did not make interpretation straightforward. Sediment records are powerful, but they are not self-explaining. They require dating, calibration, and statistical care. Yet by the 1970s, the evidence had become strong enough for a major turning point. In 1976, James Hayes, John Embry, and Nicholas Shackleton published a landmark paper showing that variations in Earth's orbit were closely tied to major climate cycles over the past several 100,000 years. It was not a perfect vindication of either Kroll or Milankovitch in every detail. Science rarely grants such tidy closure. But it was the moment when the astronomical theory of ice ages moved from elegant suspicion into something far more secure. There is a quiet beauty in the delay itself. Kroll had worked in the 19th century. Milankovitch carried the problem through the early 20th. The fullest confirmation came much later, when techniques and records finally caught up with the scale of the question. Some ideas are not rejected because they are wrong, nor accepted because they are right. They wait because the world has not yet yielded the kind of evidence needed to decide. Climate science, especially in its older history, is full of such waiting. And even at the moment of confirmation, the story retained complexity. Orbital cycles were not simple switches that turned ice ages on and off in isolation. They modulated the distribution of sunlight. Climate responded through feedbacks. Ice sheets changed reflectivity. Atmospheric carbon dioxide and other greenhouse gases shifted. The waters of the world redistributed heat and stored carbon. The astronomical theory succeeded because it offered timing and structure, not because it reduced the planet to a mechanical toy. The clock, once found, was embedded in a living system. That distinction matters. Scientists were not simply discovering an external schedule imposed on Earth from above. They were discovering a conversation between celestial rhythm and terrestrial response. A slight change in tilt or orbit might set the conditions, but the frozen parts of the planet, the atmosphere, and the waters of the world decided how strongly that change would unfold. This is one reason the theory remains so satisfying. It joins precision with contingency. Seen from that angle, Kroll becomes more interesting rather than less. He was wrong about important details, yet he sensed the essential drama early, that climate could be driven by subtle variations, and that frozen landscapes might record an immense astronomical pulse. Milankovitch refined the mathematics and focused attention on summer insolation in ways that proved more durable. Later, paleoclimate researchers supplied the evidence neither man could fully possess in his own time. No single figure solved the mystery alone. The history is cumulative, but not flat. There is also a more intimate lesson here about how scientists endure uncertainty. To live with a theory across decades, knowing it is suggestive but not fully secure, requires a specific emotional discipline. One must tolerate incompleteness without relaxing into vagueness. One must remain precise even while the evidence is fragmentary. Climate science has often attracted people of unusual patience for that reason. Its questions are vast, but its progress is incremental. By the late 20th century, the old glacial world had acquired a new order. The advance and retreat of ice no longer seemed like isolated geological episodes. They belonged to a patterned history, linked to the slow mechanics of Earth's motions through space and to the equally intricate feedbacks of climate. That changed the emotional meaning of ice ages. Ancient cold was no longer merely a lost catastrophe written into rock. It was part of a recurring planetary logic. The frozen world had a cadence. Yet that very success opened another question, one perhaps even more unsettling than the first. If small changes in incoming sunlight could help pace climate across immense spans of time, then what should scientists make of another influence entirely? One arising not from orbital geometry, but from the atmosphere itself. The search for the causes of ancient cold had carried the story into mathematics and astronomy. The next movement would begin closer to home, in the strange heat-trapping behavior of gases, and in the realization that the key to understanding ice might also lie in understanding warmth. That reversal was difficult to see at first, because it asked scientists to hold two very different intuitions in the same hand. If the long pacing of ice ages could be linked to orbital changes, then one part of the story seemed to belong to astronomy and geometry, but another part remained unresolved. Small changes in sunlight alone did not seem enough to explain the full scale of glacial worlds and their retreat, somewhere between celestial rhythm and continental ice. The Earth was amplifying, softening, delaying, and transforming the signal. To understand ice, researchers would have to understand the atmosphere in a new way. The first steps into that problem did not look, at the time, like the beginning of modern climate anxiety. They belonged to an older scientific world, shaped by laboratory discipline, the physics of heat, and a fascination with invisible processes. Heat could be felt, but it could also be measured, absorbed, redirected, and trapped. Light passed through air so freely that the atmosphere often seemed almost like nothing at all, a transparent interval between the sun and the ground. Yet transparency in visible light is not the same thing as transparency to heat. That distinction had to be discovered piece by piece. Jean-Baptiste Fourier had already raised an important question in the early 19th century. Why was Earth warmer than a simple calculation based on sunlight alone might suggest? He did not produce the modern greenhouse theory in full, but he framed the deeper puzzle with unusual clarity. The planet seemed to retain heat in a way that called for explanation. Fourier imagined the atmosphere as participating in that retention, rather than merely sitting passively above the surface. In retrospect, his insight looks almost prophetic. The person who pushed that puzzle into the laboratory most decisively was John Tyndall. In the 1850s and 1860s, Tyndall conducted experiments on gases and radiant heat with a precision that changed the subject permanently. He measured how different gases absorbed infrared radiation and found that some, including water vapor and carbon dioxide, were far more effective at trapping heat than the main bulk constituents of the atmosphere, such as oxygen and nitrogen. It sounds straightforward now. At the time, it was an extraordinary clarification. The atmosphere was not thermally neutral. Its chemistry mattered. Tyndall himself is a compelling figure for this story because he combined intellectual range with a strong sense for physical demonstration. He had the temperament of someone who wanted nature to answer under controlled conditions. In the laboratory, invisible properties could be made legible through glass tubes, heat sources, instruments, and care. There is something psychologically distinctive about that style of science. It rests on a disciplined refusal to be satisfied with intuition alone. Air feels empty. Therefore, it must be tested. Heat feels obvious. Therefore, its pathways must be measured. His conclusions also carried a historical irony. Tyndall was interested in many things, and his work on radiant heat was not a modern climate warning in the form people now recognize. But the physical principle he helped establish became one of the essential foundations for understanding both past and future climate change. A small fraction of the atmosphere, composed of gases that were invisible and often chemically minor, could exert a profound influence on planetary temperature. Once that was true, the frozen history of the Earth could no longer be understood by looking only at ice, rocks, or orbit. The sky itself had entered the story. Yet there was still a long way to go from laboratory absorption of heat by gases to a quantitative theory of climate change. That next movement came with Svante Arrhenius, whose work in the 1890s produced one of the most remarkable reversals in the history of the subject. Arrhenius is often remembered now as an early thinker about global warming, and that is correct as far as it goes. But the context matters. He was working partly from a desire to understand the causes of ice ages. The question of ancient coal drew him toward the warming effect of carbon dioxide. In trying to account for glacial change, he found himself calculating the climatic importance of heat-trapping gases. Arrhenius's 1896 paper attempted something extraordinarily ambitious for its time. He estimated how changes in atmospheric carbon dioxide could alter surface temperature across the planet. His calculations were necessarily rough by modern standards, and later generations would revise many details. Even so, the conceptual step was immense. Carbon dioxide was no longer simply one gas among many. It had become a variable in Earth history. Lower levels might help favor colder climates. Higher levels might produce warming. The atmosphere, once treated as a thin and nearly invisible envelope, had become part of the machinery that could help make or unmake an ice age. There is a kind of intellectual courage in that move worth dwelling on. Arrhenius was working at the edge of what available data, mathematics, and physical understanding could securely support. He had to combine laboratory knowledge, estimates of atmospheric behavior, and a willingness to think across scales the scientific world still struggled to hold together. That is often how foundational climate science develops. It is born not from one field alone, nor from complete evidence, but from people willing to bridge awkward distances between chemistry, physics, geology, and time. At first, however, the implications did not settle cleanly into scientific culture. Arrhenius himself did not stand in the modern role of prophet of industrial warming. In some writings, he even viewed increased warmth with a degree of optimism common to certain European scientific perspectives of the time, especially those shaped by colder northern climates and by limited foresight about global, ecological, and social consequences. Ideas often arrive before the world knows what emotional register to give them. A physical truth can be discovered decades before its civilizational meaning becomes clear. The early 20th century carried that ambiguity forward. Scientists had enough reason to suspect that carbon dioxide mattered. But the evidence for human-driven change still felt uncertain, and the atmosphere remained difficult to measure systematically over long spans. Climate itself was often imagined as a vast, self-buffering system, too large to be easily disturbed by industrial activity. Many researchers assumed that the waters of the world would absorb excess carbon dioxide with relative ease, leaving little long-term imprint in the air. In that intellectual climate, the carbon theory retained an uneasy status. It was plausible, mathematically suggestive, physically grounded, and yet still not quite real to much of the scientific world. That is why Guy Stewart Callendar matters so much in this chapter. He was not a dominant institutional power, nor the kind of scientist around whom immediate consensus naturally forms. He was an engineer with a patient mind and a taste for assembling evidence from scattered records. In 1938, he published a paper arguing that atmospheric carbon dioxide had increased due to fossil fuel combustion and that global temperatures had risen accordingly. His work now looks strikingly prescient. At the time, it sat in that familiar zone between serious warning and incomplete persuasion. Callendar's contribution feels especially human because it depended on a form of persistence that is easy to overlook. He was not discovering a new principle in the laboratory. He was gathering weather records, emissions estimates, and atmospheric measurements, trying to make an argument from imperfect pieces. This is a very different scientific temperament from Tyndall's experimental control or Arrhenius's theoretical synthesis. It is quieter, more archival, almost stubborn in its willingness to trust patterns emerging from messy data. Still, Callendar did not fully convert the field. Some scientists accepted parts of his reasoning while doubting the magnitude of the effect. Others remained attached to the assumption that the oceans would absorb enough carbon dioxide to prevent substantial atmospheric buildup. The climate system still seemed too large, too distributed, too buffered for industrial society to alter decisively. That intuition has a long history. Human beings often struggle to believe they can transform systems that appear vastly bigger than themselves, right up until the evidence grows too plain to ignore. The mid-20th century began to erode that shelter. In 1957, Roger Revelle and Hans Suess published a paper that sharply challenged the comforting idea that the waters of the world would simply swallow human emissions without consequence. They argued that the exchange between atmosphere and ocean was not a limitless cleansing process. Carbon dioxide added by fossil fuels could remain in the air in significant quantities. Their work helped shift the carbon question from a speculative possibility into something more immediate. Revelle, in particular, helped alter the tone of the discussion. He was not alone, and the shift was cumulative. But he recognized that the atmosphere and upper ocean formed a more delicate and consequential exchange system than many had assumed. The phrase often associated with this period, that humanity was conducting a large-scale geophysical experiment, remains powerful because it captures a threshold. Industrial civilization was no longer outside the climate system, observing it from a safe distance. It had entered the mechanism, yet even then, one more transformation was needed. The field required not only theory, not only suggestive compilations, but a record so precise and continuous that vagueness would become increasingly difficult to hide behind. That record arrived through the work of Charles David Keeling. His story has a very different emotional texture from those of Agassiz, Kroll, or Arrhenius. It is less about bold synthesis than about exacting measurement. Keeling had an unusual devotion to precision, the kind that can seem almost austere from the outside. He cared deeply about calibration, method, and the refusal to settle for noisy approximations when cleaner readings might be possible. In the late 1950s, Keeling established continuous measurements of atmospheric carbon dioxide, most famously at Mauna Loa in Hawaii. The location mattered, because the high-altitude site offered air less entangled with local industrial contamination than many other places. Over time, the record revealed two patterns at once. One was seasonal, a sawtooth breathing produced largely by the growth and decay of vegetation in the northern hemisphere. The other was slower and more consequential, a persistent upward climb. That curve, now iconic, did something no theoretical warning can quite do by itself. It gave history a line. There is something quietly dramatic in the discipline behind that line. Scientific change often depends on people willing to do work that appears repetitive until repetition itself becomes revelatory. Keeling's measurements mattered because they were careful enough to be trusted, long enough to reveal trend, and clear enough to turn an argument into a record. Once the rise in atmospheric carbon dioxide became visible in that way, the question was no longer whether industrial society could alter the air. It plainly had. And here, the documentary's central reversal comes fully into view. The effort to understand why ice ages had come and gone led scientists into the thermal properties of the atmosphere. That inquiry, in turn, revealed that gases could warm the planet, that carbon dioxide could shift climate, and that industrial civilization was changing atmospheric composition in real time. A search that had begun with ancient cold now illuminated modern warming. The road from glacial mystery to greenhouse physics was not a detour. It was one continuous intellectual path. That path also changed how scientists thought about orbital cycles. Astronomical variations could help pace glacial and interglacial history. But greenhouse gases offered a crucial amplification mechanism. A small initial forcing could be strengthened or weakened by changes in atmospheric composition. Climate could not be explained by sunlight distribution alone, nor could it be explained by carbon dioxide alone in isolation from orbit. Ice, albedo, and circulation. The Earth system was revealing itself as layered, interactive, and responsive in multiple directions at once. Ice and heat were not opposing topics. They were entangled parts of the same story. The broader cultural meaning of this shift took time to settle. Scientific knowledge rarely enters public imagination at the speed it enters instruments. A theory may be physically sound for decades before its emotional or political significance is widely grasped. In climate science, this delay was especially pronounced because the scales were so large and the causes so diffuse. There was no single dramatic invention, no sudden explosion, no instant when the planet visibly announced that a threshold had been crossed. Instead, there was accumulation, better measurements, better physics, better records. That slowness matters. It reminds us that understanding often arrives first as discomfort, a mismatch between what one wishes the world to be and what the evidence permits. Tyndall, Arrhenius, Callendar, Révélé, and Keeling were not all solving the same problem in the same way. They belonged to different moments, disciplines, and temperaments. Yet together, they transformed the climate story from one of ancient frozen worlds into one in which the chemistry of the air linked those vanished climates to the future of the modern one. And still, for all that progress, one challenge remained. Knowing that greenhouse gases mattered, and even knowing that atmospheric carbon dioxide was rising, did not yet give scientists an intimate record of how climate and air composition had moved together across vast ages. To see that more directly, the field would need another archive, colder, quieter, and stranger than any observatory or weather station. It would need a place where ancient atmospheres had been kept, layer by layer, inside the frozen world itself. That archive had been waiting in plain sight, though for a long time, almost no one understood how much it contained. A glacier could already be read in the old geological sense, through its marks on stone and the debris it carried down from higher ground. But to imagine that the ice itself might hold a detailed memory of past climate required a different leap. It meant treating frozen layers not as inert accumulation, but as preserved history. Snow fell, was buried by newer snow, compressed, altered, sealed, and carried downward through time. Somewhere in that quiet descent, the atmosphere of vanished centuries might still remain. The first part of that realization did not begin with grand drilling programs or giant international collaborations. It began with a subtler thought about water itself. In the early 1950s, the Danish scientist Willy Dansgaard became interested in isotopes in precipitation, in the slight differences among water molecules that arise because not all atoms of oxygen or hydrogen have exactly the same mass. These differences are minute, invisible to the eye, and easy to dismiss as technical detail. Yet in science, technical detail sometimes opens into a new world. Dansgaard saw that rain and snow did not carry isotopic signatures at random. Their proportions varied with temperature and with the processes by which water evaporated, condensed, traveled, and finally fell back to Earth. It was a beautiful discovery because it began from something almost absurdly small. A drop of water does not announce its history. Snow falling over Greenland appears, to ordinary perception, as weather and whiteness and cold. But in its molecular structure, it carries traces of the conditions under which it formed. Heavier isotopes behave slightly differently from lighter ones as water moves through the atmosphere. Over great distances and repeated phase changes, those small preferences accumulate into meaningful patterns. By measuring those patterns with care, Dansgaard realized one might infer the temperature conditions associated with the snowfall that had once formed a layer of ice. The power of that idea was not immediately obvious outside a narrow scientific circle. Isotopes are not naturally dramatic. They belong to the realm of careful laboratory work, of ratios and standards and calibration. Yet that is exactly why the breakthrough mattered. Climate science had long struggled with the gap between grand theories and fragmentary evidence. Here, in principle, was a way to recover a continuous record from the frozen world itself. A snowflake falling in one age could, after burial and compression, carry a measurable relation to the climate of that age, if enough layers survived. Stacked year upon year and century upon century, then ice could become something astonishingly rare in Earth history, a natural archive that was both physical and chronological. Dansgaard had the temperament to follow such an idea where it led. He seems to have possessed a combination that can look contradictory from the outside. Imaginative reach joined to experimental restraint. He was willing to believe that a vast climate history might be encoded in tiny isotopic shifts, but equally committed to proving that belief with hard measurements. In his work, boldness and caution strengthened each other. As the method developed, ice began to look different. A glacier or an ice sheet was no longer only frozen water stored on land, or a dynamic mass that shaped landscapes and influenced sea level. It had layers. Those layers had sequence. That sequence had chemistry, and the chemistry had memory. Once that chain of thought took hold, the white expanses of Greenland and Antarctica changed their scientific character. They were no longer simply remote environments to be crossed, mapped, or feared. They were libraries, though libraries of an unusual kind, silent, fragile in their own way, and readable only through extraction. Extraction, of course, is where the romance of scientific insight collides with logistics. It is one thing to imagine a climatic archive inside ice. It is another to recover a clean cylinder of that archive from depth. Transport it, preserve it, cut it, and analyze it without losing what makes it valuable. Ice core science was born at the intersection of theory, field engineering, and raw endurance. Researchers had to drill in places where cold, remoteness, mechanical failure, and human fatigue could easily turn elegant ideas into stalled machinery. The archive was real, but it did not yield itself gently. Greenland became one of the great proving grounds for this new kind of science. The reasons were practical. Its ice sheet was accessible compared with Antarctica, yet still large and old enough to preserve long records. It offered a vast body of layered snow and ice whose upper surfaces continued to receive annual deposition. If the layering could be traced and sampled deeply enough, one might move backward through climate history the way a dendrochronologist moves through tree rings. Though the analogy is only partial, ice has its own complications. Layers thin with depth, flow distorts sequence, melt can blur detail. Yet the underlying hope remained irresistible. The Cold War gave this scientific ambition a strange and unmistakably 20th century setting. Polar regions had become strategically interesting as well as scientifically compelling. Routes across the Arctic mattered to military planning. Ice sheets became laboratories, engineering challenges, and geopolitical spaces all at once. Camp Century in northwestern Greenland emerged from this entanglement. Built under the ice in the late 1950s and early 1960s by the U.S. Army, it was officially a research station and test site for Arctic engineering. It also existed within a broader military logic that included ideas about mobility, infrastructure, and, in secret planning, even missile deployment beneath the ice. Viewed from a distance in time, Camp Century feels almost surreal. A climate archive was being approached through a world shaped by nuclear rivalry, strategic anxiety, and ambitious engineering in one of the coldest inhabited places on Earth. Men lived in carved tunnels beneath snow and ice, surrounded by generators, instruments, and the continuous labor of keeping systems alive in a place that resisted every human presumption of permanence. It is a reminder that science rarely unfolds in isolation from the wider atmosphere of its age. Yet amid that larger setting, the scientific significance of deep drilling was real and lasting. In 1966, an ice core recovered at Camp Century reached bedrock, producing one of the earliest deep records from the Greenland ice sheet. This did not instantly solve every climatic question, and later reinterpretations would refine or challenge aspects of what scientists thought they saw in the deepest parts of the core. But the achievement mattered enormously. It proved that very old sequences could be obtained. The archive was no longer hypothetical. Once cores began to arrive in laboratories, another transformation followed. Ice had to be read with care, equal to the effort required to recover it. Visual stratigraphy could reveal layering and impurities. Dust concentrations could hint at windiness, dryness, and atmospheric transport. Electrical properties, trapped particles, volcanic ash, and chemical markers all offered different kinds of evidence. Most remarkable of all were the tiny bubbles of ancient air enclosed as snow turned, over time, into firn and then dense glacial ice. Those bubbles made the subject feel almost uncanny. Here were actual samples of former atmospheres, preserved across tens of thousands of years. The past was no longer inferred only through indirect proxies. It could, in a limited but very real sense, be sampled. That intimacy changed climate science profoundly. An ice core brought something close to the air itself. Scientists could analyze carbon dioxide and methane trapped in bubbles, compare those concentrations with isotopic temperature proxies, and watch the relationship between atmosphere and climate move together through time. The earlier arc of the story, from Tyndall's heat-absorbing gases, to Arrhenius's calculations, to Keeling's modern measurements, suddenly extended backward into deep history. Ancient atmospheres had been waiting in the ice all along. This did not make the reading simple. One of the subtleties of ice core science is that the age of the surrounding ice and the age of the gas enclosed in its bubbles are not exactly the same. Snow remains porous for a time as it compacts, allowing air exchange before the pores close off and seal a sample of the atmosphere. That means climate proxies measured in the ice matrix and gas concentrations measured in the bubbles must be aligned with care. Even when the archive is astonishingly rich, it still requires chronology, interpretation, cross-checking, and restraint. As the field matured, Greenland and Antarctica each began to reveal different strengths. Greenland offered records with high temporal resolution and dramatic sensitivity to North Atlantic climate changes. Antarctica, with its massive and more slowly accumulating interior ice, opened longer windows into Earth history. Drilling projects multiplied, methods improved, and international collaboration deepened. To drill an ice core is to turn depth into time, to lower machinery through frozen layers until the present has been replaced by sequences laid down before nations, before cities, before agriculture in some cases, and eventually before recorded history itself. There is also a very human feeling that emerges around such archives. Reading an ice core means accepting that the atmosphere has a biography. The air around us appears immediate and transient, always moving, always mixing, impossible to grasp. Yet in ancient ice, it becomes historical. It can be dated, compared, and followed through cycles of cold and warmth. The climate system, once reconstructed through scattered evidence and elegant theory, becomes startlingly concrete. One can see carbon dioxide falling and rising. One can see temperature proxies shifting. One can place them side by side. By the late 20th century, this changed the emotional and intellectual texture of climate research. Theories that had once relied heavily on indirect reasoning could now be tested against direct paleoclimatic records of extraordinary quality. Orbital cycles, greenhouse gases, dust, volcanic events, and regional temperature changes were no longer parts of separate conversations. In the ice, they met. The great advantage of ice core science was not merely that it provided long records. It was that it braided together multiple dimensions of past climate into one archive. For scientists, this was both exhilarating and humbling. Exhilarating, because questions that had once felt almost philosophical suddenly acquired measurable answers. Humbling, because the climate system revealed itself as even more intricate than expected. Ice cores showed tight connections between greenhouse gases and temperature across glacial cycles. But they also showed lags, feedbacks, abrupt shifts, and regional differences that made any simple account feel inadequate. The archive spoke clearly enough to transform the field, yet subtly enough to resist reduction. The psychology of working with such material must have been unusual. Imagine spending years with samples whose upper layers correspond to recent centuries, then descending into portions laid down when mammoths still walked, or when vast ice sheets ruled northern continents. Analysis becomes a form of time travel stripped of fantasy and forced into rigor. A scientist does not visit the past in any romantic sense. One dissolves, measures, calibrates, compares, and tries to remain disciplined while handling matter older than memory. At the same time, the field retained its dependence on physical courage and environmental exposure. Ice core science was never purely a laboratory discipline. The people who interpreted ancient air relied on teams who could work in punishing cold, maintain drilling systems far from ordinary supply lines, preserve samples under conditions where contamination or warming could ruin them, and repeat difficult operations year after year. The archive was scientifically delicate, but the effort required to reach it was rugged and material. Once the public imagination caught a glimpse of ice cores, the frozen world acquired a new symbolic role. Glaciers and ice sheets had long stood for distance, danger, purity, endurance, even emptiness. Now they also stood for testimony. They had become witnesses to climates no human had lived through. Their authority did not come from majesty or remoteness. It came from preservation. Cold had kept records that warmer parts of the world often erase. And yet the most unsettling consequence of this new archive was still gathering beneath the surface. Researchers expected long cycles, broad swings, and glacial rhythms paced by orbital change and amplified by greenhouse gases. Those patterns were there, but as the cores improved and their resolution sharpened, the frozen record began to show something else as well, something less comfortable than a slow planetary breathing. Buried within the layers were signs that climate had sometimes shifted with startling speed. The archive had begun by speaking. Soon, it would do something even more surprising. It would speak quickly. The archive had spoken clearly enough to confirm long cycles, broad glacial rhythms, and the intimate relationship between temperature and the chemistry of the air. That alone would have changed climate science. But once the cores grew longer, cleaner, and more finely resolved, a different kind of disturbance entered the story. The layers did not always unfold with the calm pace many researchers had expected from the old image of Earth history. In some intervals, the record seemed to flicker. Climate did not only drift. At times, it lurched. For a long while, the deepest habits of geological thinking had favored slowness. There were good reasons for that. Mountains erode gradually. Continents shift almost imperceptibly. The waxing and waning of great ice sheets had already trained scientists to think in spans of tens of thousands of years. Even those who accepted that climate could alternate between glacial and interglacial worlds often pictured those transitions as majestic and prolonged. That picture was never wholly wrong. Large climate changes often do unfold across immense durations, but it turned out to be incomplete in a way that mattered deeply. In Greenland especially, where annual layers could sometimes be resolved with remarkable precision, the ice began to reveal episodes that did not fit the gentler expectation. During the last glacial period, the record showed repeated abrupt warmings, followed by more gradual coolings, oscillations that later came to be known as Dansgaard-Oeschger events. Temperatures over Greenland could swing sharply in what looked, in geological terms, like astonishingly short intervals. The broad rhythm of the Ice Age remained intact, yet nested within it were pulses and jumps that felt far more restless than the older picture of climate had allowed. That pattern was difficult to absorb at first because it challenged more than one scientific instinct. Researchers had worked hard to extract order from the frozen record. Orbital cycles provided one kind of order. Greenhouse gases provided another. What the Greenland cores now suggested was that the climate system also possessed internal thresholds and modes of reorganization. It could move from one state to another with a speed that seemed out of proportion to the slow forcing in the background. The Earth was not simply following a smooth script. It could hesitate, snap, and settle into a different arrangement. That insight changed the emotional texture of paleoclimate research. A world that shifts gradually is conceptually demanding, but in a strangely calming way. It gives the mind time. A world that can jump is harder to live with, even as an intellectual possibility. It introduces the idea that large systems may contain hidden instabilities, that continuity at the surface can conceal strain beneath it, and that the pace of change is not always dictated by the scale of what is changing. A great ice sheet may take millennia to build, yet circulation patterns or regional climates connected to it may rearrange much faster. Among the most influential episodes in this new way of thinking was the Younger Dryas, near the end of the last ice age. As the world was warming and large northern ice sheets were retreating, climate in the North Atlantic region abruptly turned colder again. In Greenland, this reversal appears with striking clarity in ice core records. Then, after roughly a millennium of that colder interval, the return to warmer conditions appears to have happened with extraordinary speed. Later estimates suggested that Greenland temperatures may have risen by something like 10 degrees Celsius in about a decade at the end of the Younger Dryas. Even allowing for regional specificity and caution in interpreting exact figures, the larger message was unmistakable. Climate did not always need millennia to change its character. The Younger Dryas mattered, not simply because it was dramatic, but because it looked like a historical argument preserved in ice. Scientists had before them a case in which warming had been interrupted, cold had returned, and then warmth had resumed, all within the broader deglaciation that followed the last glacial maximum. This was not a minor fluctuation. It was a reorganization large enough to leave traces across the North Atlantic world and beyond. Lakes, pollen records, marine sediments, and glacial evidence all joined the conversation. Paleoclimatology was no longer only the study of slow sequences. It had become the study of abruptness as well. Naturally, explanation lagged behind recognition. One influential idea connected the younger Dryas to meltwater released from retreating northern ice sheets. If enough fresh water poured into the North Atlantic, it could weaken the overturning circulation that helps transport heat northward. A reduction in that transport could cool large regions around the North Atlantic basin, even within a globally warming world. Wallace Breaker, among others, helped popularize the importance of circulation in abrupt climate thinking. The image of climate as a conveyor system, while imperfect in detail, gave both scientists and the public a way to picture how a large but vulnerable circulation might be disrupted. Yet, like many powerful scientific stories, this one has never been entirely simple. There has been long debate over the exact sources, routes, and timing of meltwater involved in the younger Dryas. Researchers have argued over whether the discharge came chiefly from glacial Lake Agassiz or related proglacial systems, how the water was routed, and whether freshwater forcing alone fully explains the transition. Evidence has shifted with new data. Some proposed pathways have looked less secure over time. Others remain plausible. The larger lesson has endured even as details remain contested. Abrupt climate change is real, but the mechanisms that trigger a specific event can be difficult to reconstruct with confidence. This combination of certainty and uncertainty is part of what made the field so fertile. Scientists were no longer debating whether the record contained sharp transitions. They were debating how a system of air, ice, currents, salinity, and heat could cross thresholds so quickly. Some hypotheses emphasized freshwater pulses. Others explored sea ice feedbacks, atmospheric circulation shifts, or combinations of mechanisms that interacted non-linearly. The language of feedback, tipping, and mode change became harder to avoid. Climate could no longer be imagined as a smooth dial turned steadily by external forcing. This altered how researchers thought about the end of the last ice age more generally. Deglaciation had once seemed like the great slow release from a glacial world. It still was that, but now it also appeared punctuated by bursts, pauses, and reorganizations. One of the most striking examples lay not in temperature alone, but in sea level. Meltwater Pulse 1A, a period during the last deglaciation, is widely interpreted as an episode of very rapid global sea level rise. The exact magnitude and source distribution remain debated, but the event appears to represent around 20 meters of global mean sea level rise in roughly 5 centuries. That is nowhere near overnight. Yet in geological terms, it is astonishingly fast. Here again, the record changed the scale of what scientists felt able to imagine. 20 meters in 500 years means a world in which coastlines would retreat across generations. Not eras, estuaries, deltas, islands, and continental shelves would be transformed within spans that human communities could experience historically, if not instantaneously. The thought experiment that opened this documentary, All the Ice Gone by Morning, remains physically impossible. But events like Meltwater Pulse 1A brought the emotional horizon of change closer. They showed that the Earth system, under deglacial conditions, had already produced episodes of sea level rise far swifter than the old leisurely picture of post-ice age change had encouraged people to expect. And yet the detective work around that event is still unfinished. Scientists continue to debate how much of the water came from the Laurentide ice sheet in North America, how much from Antarctica, and whether additional sources contributed. Coral records, sea level markers, isotopic data, glacial modeling, and sedimentary evidence all play roles in the argument. The uncertainty here is not embarrassing residue. It is a reminder of how difficult it is to trace planetary water redistribution after the fact. Even when the signal was enormous, these unresolved questions had an important psychological effect on the field. They trained scientists to take abrupt change seriously without pretending every mechanism had been neatly solved. That discipline matters. There is a temptation, especially when an idea is alarming, either to overstate certainty for dramatic effect or to dismiss it because some details remain unsettled. Paleoclimate research matured by refusing both temptations. It learned to say, with increasing confidence, that major climate reorganizations can happen quickly, even while acknowledging that the exact sequence of triggers and feedbacks in a given case may remain partly obscure. The Greenland cores pushed that discipline further as resolution improved. The record of abrupt warmings during the glacial period did not look like a single curiosity, but like a recurrent mode of behavior. Climate had more than one pace. Sometimes it followed the long cadence of orbital forcing. Sometimes it expressed the slower partnership between greenhouse gases and ice volume. And sometimes, within those broader structures, it jumped once that possibility entered the field. The older assumption of a uniformly gradual climate past could no longer be maintained. Sudden change was not a rare accident. It was part of the system's repertoire. That realization spread outward into neighboring disciplines. Oceanographers began paying renewed attention to circulation thresholds and fresh water forcing. Atmospheric scientists considered how shifts in sea ice, storm tracks, and pressure patterns might amplify or extend regional changes. Geologists and paleoecologists re-examined records on land for signals once dismissed as noise or local anomaly. Climate modelers faced a new challenge as well. It was no longer enough for a model to reproduce long-term averages. It had to be capable, at least in principle, of representing a world in which feedbacks and abrupt transitions could matter. There was also a deeper change in historical imagination. Earlier sections of this documentary followed how scientists learned to think of climate as dynamic, then rhythmic, then chemically responsive. Abrupt change added a more unsettling layer. It suggested that stability itself might be more contingent than it appears from inside a relatively stable period. Human societies build expectations from the recent past because that is what experience offers. Rivers tend to flow where we remember them. Seasons feel patterned. Coasts appear dependable enough to urbanize. Infrastructure, law, agriculture, and cultural memory all lean on recurrence. Abrupt paleoclimate evidence whispered that recurrence can mislead. That is partly why the discovery mattered beyond academia. It was not simply an additional fact about old ice. It was a challenge to a civilizational instinct. Modern societies are comfortable with change that is either very slow or very local. They are much less comfortable with the possibility that large systems may flip faster than institutions can adapt. The paleoclimate record did not say that every component of the Earth system behaves this way, or that all present changes would mimic younger Dryas dynamics, but it broke a psychological barrier. At the same time, the field had to guard against a different misunderstanding. Abrupt does not mean magical. A rapid shift in climate is still prepared by conditions, feedbacks, and physical constraints. There is no need for melodrama. The value of abrupt climate science lies precisely in its realism. It shows how a complex system can contain thresholds, lags, and sharp reorganizations without violating the laws of physics. It asks us to exchange the comfort of linear intuition for a truer, more complicated picture. Once that picture takes hold, The impossible opening premise of this film begins to function differently. It becomes a disciplined way of asking what frozen systems are holding back, how quickly some consequences can unfold once change begins, and where the most important thresholds may lie. By the late 20th century, climate science could no longer be narrated as the study of gentle trends alone. The great frozen archives had introduced tempo as a scientific problem. How fast can temperature shift in a region? How fast can circulation weaken or reorganize? How quickly can shorelines respond when deglaciation accelerates? Which parts of the system move slowly because they are massive, and which move quickly because they are linked by feedback to those massive components? These questions did not all have final answers, but they reshaped the conversation irreversibly. They also made the cryosphere more conceptually central than ever. Ice was not merely evidence of climate. It was participant, amplifier, and in some cases gatekeeper. Meltwater could alter circulation. Sea ice could influence reflectivity and heat exchange. Ice sheets could restrain vast quantities of water whose release would affect coasts across the globe. Overnight melt remains impossible, but the underlying lesson is no longer abstract. Earth has a history of moving faster than older science expected. And once that lesson had settled into the field, another question followed almost of its own accord. If past climates could jump, if large ice losses could produce episodes of rapid shoreline change, if the atmosphere and frozen regions were tightly coupled, then how should scientists read the modern world? A world in which greenhouse gases were rising, measurements were improving, and some researchers were already warning that parts of Greenland and Antarctica might prove less stable than they looked from a distance. The record of abrupt change had prepared the mind. The next step was to bring that sharpened understanding back to the present, and to ask what the impossible question at the beginning of the film was really trying to show us. By the time that possibility came into view, the opening question of the documentary had already changed its shape. At first, what happens if the ice caps melt overnight sounded like an invitation to imagine spectacle. Coastlines erased by dawn, cities waking to a geography they no longer recognized. The world transformed in a single stroke. But once scientists learned that climate can shift abruptly, that frozen systems are tied to circulation, feedback, and thresholds, the question stopped being childish in quite the same way. It became a pressure test for the imagination, not because the event itself could literally occur, but because it forced people to ask what those distant masses are holding in place, and how much can begin to change long before all of the ice is gone. That return to the present did not arrive as a single revelation. It came through a series of warnings, measurements, and uncomfortable reinterpretations of what stability means when viewed across the timescales of glaciology. One of the clearest early voices in that shift was John Mercer, a glaciologist whose work carried him across some of the coldest and most remote regions on Earth. Mercer had the kind of scientific life that now feels emblematic of a certain generation of polar research. Field-hardened, physically demanding, shaped by direct engagement with ice rather than abstraction alone. He worked in Antarctica, Greenland, Alaska, and South America, and he understood from experience that ice sheets are not inert monuments. They are structures under stress. In 1978, Mercer published a paper that would later seem uncannily early in its implications. He argued that the West Antarctic ice sheet might be particularly vulnerable to the greenhouse effect. That warning mattered because West Antarctica is not simply a high frozen plateau sitting securely above sea level. Much of it rests on bedrock lying below sea level. which means the geometry of the ice sheet itself can create a special kind of instability. Ice grounded below sea level and extending outward toward floating shelves is vulnerable in ways that are not obvious from a map. If warm water reaches the undersides of ice shelves and weakens them, the shelves can lose some of the buttressing force that slows the inland ice behind them. Grounding lines can retreat. In certain configurations, retreat into deeper basins can become self-reinforcing. Mercer understood enough of that geometry to feel where the danger lay, even though the tools available to him were far more limited than those available today. This is one of the recurring patterns in the history of science. Some researchers grasp the meaning of a system before they can measure every part of it cleanly. They sense the structure early, sometimes from physical intuition sharpened by field experience. And the full evidentiary machinery arrives later. That does not make them infallible. But it does mean their warnings can sound uncomfortably large before the world has learned how to hear them. Mercer was, in fact, described by some as an alarmist. That label has a revealing history. In science, it is often applied to people whose conclusions arrive before the broader culture has decided how to absorb them. Sometimes the label is deserved. At other times, it reflects a more psychological resistance, an unwillingness to let a physically grounded warning alter one's emotional sense of the possible. Mercer's case sits close to the second category. He was not inventing a cinematic catastrophe. He was reading a vulnerable ice sheet in the light of greenhouse warming and recognizing that the consequences, though slow by human standards, could be enormous by civilizational ones. This is where the documentary's title question becomes most useful. The fantasy version imagines all the ice gone by sunrise. Mercer's world was stranger and more difficult. The real danger was not instant annihilation. It was commitment. A system could be nudged, weakened, set on a path of retreat, and still take centuries or millennia to unfold fully. By the time the largest visible consequences arrived, the conditions making them increasingly hard to avoid might have been established long before. Human attention is poorly designed for this kind of danger. We are alert to explosions, collapses, and sudden impacts. We are much less skilled at feeling the weight of long processes once they have crossed into inevitability. To understand why this mattered so much, scientists had to think carefully about how ice actually retreats or fails. For much of the public, an ice sheet sounds like a single frozen block. In reality, it is an organized system with margins, flow lines, outlet glaciers, floating shelves, accumulation zones, and areas of thinning or acceleration. Antarctica especially complicated ordinary intuition. East Antarctica contains a colossal mass of ice, much of it comparatively stable on short timescales, though not immune to change. West Antarctica, by contrast, drew special attention because of its marine character, its bedrock geometry, and the role played by surrounding ice shelves. As the 20th century moved toward its close, researchers began to accumulate more evidence that some of these concerns were not theoretical curiosities. Glaciers feeding Antarctic ice shelves could speed up. Shelves themselves could weaken or collapse. Greenland, too, began revealing changes in surface melt, outlet glacier behavior, and mass balance that invited more serious long-term concern. None of this resembled the drama of an overnight melt. The changes were distributed, often regionally uneven, and dependent on mechanisms that required careful explanation. Yet their significance lay precisely in that quietness. Science was learning to recognize destabilization before total loss. Then came the age in which the ice could be weighed from space. There is something almost impossible seeming about that sentence, especially when placed beside the 19th century beginnings of glacial theory. Agassiz had argued from polished stones and transported boulders. Later generations had drilled cores, mapped thickness, tracked margins, and refined the physics of ice flow. But with satellite gravimetry, most famously through the Grace and Grace follow-on missions, scientists gained the ability to infer changes in Earth's gravity field caused by shifts in mass. In practice, this meant that Greenland and Antarctica could be monitored for net mass loss over time, in a way earlier researchers could scarcely have imagined. The remote frozen worlds no longer had to be understood only through expedition, sparse stations, or intermittent surveys. They entered a new observational regime in which loss itself could be tracked with planetary continuity. That did not make the science simple. Interpreting gravimetric data requires care. One must separate mass changes due to ice from signals related to groundwater, land processes, or the slow rebound of crust once pressed down by ancient ice. Satellite altimetry, interferometric methods, field measurements, and modeling all remain part of the picture. But together, they changed the evidentiary atmosphere around ice sheet science. The question was no longer whether Greenland and Antarctica mattered, nor whether they could change. It was whether the rates, patterns, and long-term commitments implied by observed change were being adequately understood. Greenland began to reveal a story of surface melt, runoff, and dynamic loss through fast-moving outlet glaciers. Warmer air over the ice sheet increased melting at the surface, while changes in glacier flow contributed additional loss in some sectors. Antarctica offered a story more uneven in space, yet equally consequential. In parts of West Antarctica, warm water intruding onto continental shelves could reach grounding zones and the undersides of floating ice shelves, thinning them from below. Pine Island and Thwaites glaciers, among others, became familiar names, not because they were suddenly collapsing in a single moment, but because they occupied positions within a vulnerable system whose retreat could matter far beyond their immediate geography. This is one of the subtle truths the thought experiment at the beginning of the film was always trying to reach. A coastline in Miami, Mumbai, Lagos, Shanghai, Alexandria, or Rotterdam is connected to processes unfolding in places that look nothing like those cities. Warm water moving beneath Antarctic ice shelves, summer melt darkening parts of Greenland, snowfall variability over the polar interior, grounding line retreat in a remote embayment. These do not resemble ordinary urban causes. They do not announce themselves in the language of daily life, and yet, over long enough spans, they are among the most important determinants of what future coastlines will be. Here the language of deep uncertainty enters, and it deserves careful handling. In ordinary conversation, uncertainty often sounds like weakness, as though scientists are admitting they do not know enough to say anything meaningful. In ice sheet science, uncertainty often has a more precise and more sobering meaning. Researchers know quite a lot. They know warming affects ice sheets. They know Greenland and Antarctica have been losing mass. They know higher sustained warming implies greater long-term ice loss and higher eventual sea level. They know some mechanisms of instability and can model them to a degree. Yet because the systems are large, nonlinear, and sensitive to bed geometry, ocean conditions, and feedbacks, the upper ends of long-term loss remain difficult to constrain with high confidence. Uncertainty here does not soften the warning. It sharpens it. This is why major assessments have framed parts of the sea level future in carefully qualified but unmistakably serious terms. At sustained warming levels, around 2 to 3 degrees Celsius above pre-industrial conditions, Greenland and large parts of West Antarctica are thought likely to face very long-term, effectively irreversible loss on multi-century to multi-millennial timescales. That language can be easy to mishear because the timescales are so extended. Many people mentally file millennia under "not my problem." But that reaction misses the more unsettling point. The eventual scale of change and the time scale of commitment are not the same thing. A society living in 1 century can help determine the shoreline conditions of many centuries to come. This distinction between realized change and committed change may be the deepest answer to the impossible question that began the film. If all the great land ice vanished overnight, coastlines would indeed be transformed beyond any modern experience. But that cannot happen. What can happen? And what climate science has been trying to teach with increasing patience is that irreversible trajectories may begin while the world still looks largely recognizable. The map may hold for a while. Cities may continue to function. Flood defenses may be raised. Wetlands lost gradually. Nuisance flooding normalized. Insurance systems strained. Groundwater salinized. And retreat debated in slow political language. Meanwhile, in the background, the larger cryospheric commitments continue to accumulate. There is something profoundly difficult for the human mind in that structure of time. We are storytellers by instinct, and stories tend to grant significance to events that are visible, bounded, and immediate. Ice sheet change often denies us that comfort. Its early stages are statistical, observational, inferential. A line slopes upward. A satellite record lengthens. A glacier retreats year by year in ways that mean little to anyone not watching closely. The meaning is real before it is dramatic. Science, at its best, extends perception into precisely those regions where instinct fails. And so the opening fantasy of instant melt now appears less useful as a prediction than as a moral and intellectual lens. It stripped away one illusion, that the frozen parts of Earth are merely decorative or remote. Then history stripped away another, that climate is naturally stable on the scales that matter to civilization. Paleoclimate removed a third, that all large changes must be slow. Modern observation removed a fourth, that the great ice sheets are beyond contemporary human influence. What remains, after all those illusions have been cleared, is a world in which frozen masses still occupy the edges of the map, but no longer the edges of understanding. The transformation in human knowledge here is easy to underestimate because it unfolded gradually. Over 2 centuries, scientists moved from reading glacial scratches on rock to imagining orbital rhythms, to discovering the heat-trapping power of gases, to recovering ancient air from ice, to tracing abrupt climate shifts, to monitoring present-day mass loss from orbit. Few scientific stories offer such a complete change in perspective. Ice began as scenery, obstacle, and extremity. It became archive, actor, and warning. If the documentary has circled back to that question now, it is because the real meaning of an overnight melt lies in what it teaches us to notice while the night has not yet ended. The world does not need every ice sheet to vanish in a single impossibility for coastlines to become unstable, for future generations to inherit transformed boundaries, or for civilization to discover that permanence was partly a borrowed condition. Frozen things do not have to disappear completely to stop holding the world in the same shape. And perhaps that is where the most unsettling calm of the subject resides. The poles are still there. Greenland is still there. Antarctica is still there. The great white masses have not vanished between one evening and the next. Yet they are no longer scientifically silent. And they are no longer emotionally remote. They have entered history in a new way. They are being measured, compared, modeled, argued over, and watched. Their future is not entirely known. Their importance is no longer in doubt. The thought experiment that once sounded like fantasy has led, by a long path, to a truer understanding of reality, one in which the gravest transformations need not be sudden to be immense, and need not be complete to begin. By the end of a question like this, the image that tends to remain is not the one people expect. Not only water climbing over shorelines, or cities marked in blue, or the sudden violence of a world transformed. What remains more deeply is the realization that ice has never been just a frozen boundary at the edge of human life. It has been part of the planet's hidden balance, storing weight, memory, and time in forms so immense that they are easy to mistake for permanence. That may be what makes the subject linger in the mind. Something can look motionless for longer than civilizations have existed and still be part of a living system, quietly helping hold the shape of the world together. There is also something deeply human in the way this truth was uncovered. No one ever stood in one place and understood it all at once. One scientist studied scratches in stone. Another measured the strange behavior of gases. Another drew a cylinder of ice from the deep cold and found that ancient air had been waiting there all along. Piece by piece, century by century, human beings learned to read what had once seemed unreadable. That may be one of the gentlest patterns in the history of science. Nature does not often reveal itself in grand declarations. More often, it yields through patience, through doubt, through careful attention to things that at first appear silent. And so the lasting meaning of this story may not lie in the impossibility of ice caps melting overnight, but in the quieter truth beneath the question. We live in a world supported by processes too large to see in a single lifetime, yet delicate enough to be altered. To understand that is not only to know something about ice, it is to feel, with a little more clarity, how strange and interwoven this planet has always been, and how much of it still waits to be understood